Okay, the Rutherford gold foil scattering experiment. Basically what Rutherford did was, instead of taking like a sheet of aluminum foil, he used gold foil, and it was so thin that basically when he first started to do this experiment, he didn't think anything was going to happen to these alpha particles that he shot through. So basically, a alpha particle was shot through the gold foil, and basically there was a screen set up over here, and Rutherford thought that perhaps he would learn something about the gold foil when he shot the alpha particles through, but what he found out was beyond his wildest expectations. So before we get into this actual experiment, let's talk a little bit more about these alpha particles and where the heck do these alpha particles come from. So let's step back and go back and talk about how there were certain rocks that were found, and these special rocks it was discovered actually by accident that these special rocks were giving off something, as they sat around. Something actually was being given off. And the way it was figured out was certain scientists threw one of these rocks into a drawer that had some undeveloped film in the drawer. And basically, the next time the drawer was opened up, all over the film were like these white splatches of stuff. And the only thing that could possibly be going on was that that white splatches of stuff was coming from these special rocks. And these special rocks at this time were just like carried around in people's pockets and all. And what they were actually carrying around were radioactive rocks like uranium. And many of these scientists end up, having health problems and actually dying young because they didn't realize the dangers that they were dealing with. So basically, the question was, what is this invisible stuff being given off of these special rocks, like uranium? So scientists, being ever experimenters, they were trying to figure out what experiment they could do to figure out what this invisible stuff was. So a lead container was made, and some of these special rocks were put in that container. And a little hole was left in the container for the invisible stuff that was coming off the rocks, to exit out of the little hole like that. And one of the questions the scientists had, was, is that invisible stuff charged? Is it positively charged? Is it negatively charged? Is it neutral? So, oppositely charged parallel plates were set up, One metal plate was charged positively, the other charged negatively. And when the stream went through the oppositely charged plates, it immediately broke up into 3 smaller streams. Some of the stuff went straight through. Some of the stuff got deflected upward big time. Some of the stuff got deflected downward a little bit. Of course, as soon as it went out of the plates, this should be a straight path here, and this should be a straight path here. Because it no longer would deflect once it came out of the plates. And again, no one knew what these 3 streams were, so they just basically gave them letter names. Like maybe today we would call them X, Y, and Z. But back then they used Greek letters, and they used alpha, beta, gamma. And the particles that deflected downward, they were called alpha rays. And the particles that went straight through were called gamma rays. And the particles that got deflected upward were called beta rays. And basically, due to the way they got deflected, since the gamma rays went straight through, scientists pretty much figured out that they were neutral. The beta rays that got deflected towards the positive plate must have been negatively charged. And the alpha particles that got deflected towards the negative plate must have been positively charged. And notice how the beta particles, they got deflected a lot more, indicating that they had a lot less mass. But for the most part, this is what was known about these 3 streams of invisible stuff coming off of these special rocks. Now, today we know that beta rays sometimes they're called beta particles. And remember, now with the wave particle duality of nature, sometimes you can think of it as a particle, sometimes you can think of it as a wave. But nonetheless, these are electrons. The gamma rays that went straight through Again, you can think of them as gamma particles. These are high frequency photons, high frequency light. And the alpha particles that were positively charged and deflected downward, these are the nuclei of helium atoms. Nuclei is just the plural of nucleus. You wouldn't say nucleuses, so you would say nuclei. These are the nuclei of helium atoms. And that's what Rutherford used in his gold foil experiment. These alpha particles, or alpha rays. If you take a helium atom in its nucleus, it has 2 protons, 2 neutrons. If it's neutral, it has 2 electrons orbiting. If you strip those electrons away off of the helium atom, then you would just be left with the nucleus of the helium. And that's what an alpha particle was. Just the nucleus of the helium atom. Notice they're pretty massive little nuggets. Neutrons are neutral, but the protons each have a charge of +1. So basically, charge of alpha particle equals +2 elementary charges. So by taking a piece of radioactive rock, putting it through oppositely charged plates, basically Rutherford would only use this stream right here. And this is the stream that he shot through the gold foil. Now, of course, Rutherford didn't do this experiment himself. As most professors, when you get to that level, you had your graduate students do your grunt work for you. So Rutherford had 2 of his students working in the basement of a building, shooting these alpha particles through gold foil, bored out of their minds. Because basically, no matter where they shot the alpha particle through, the alpha particle would just go straight through. So basically, if they shot the alpha particle through right here, it would go through right there and light up a little dot on the screen, just like a TV screen. A little tiny pixel would light up right there. If they shot the alpha particle through over here, it would just go through right there. If they shot it through here, it would just go through straight there. If they shot it here, it would just go straight through. Let's make that straight. Whoa. One of these 2 students, his last name was Geiger. He went on to become famous for Geiger counters, which measure invisible radioactivity. So like in Japan, they use Geiger counters to see how the radiation level around that nuclear power plant is doing. But nonetheless, Geiger and his fellow classmates, they were just students, and they were so bored because no matter where the alpha particle was shot through, it just went straight through. They told Rutherford, nothing's happening here. Rutherford basically said, get back down in that basement, keep taking measurements. And lo and behold, after enough trials, basically an alpha particle was shot through and it was slightly deflected. Every once in a while, there would be an alpha particle deflected. Every once in a while, there might be an alpha particle shot through at just the right spot, and it might be a little bit deflected. So Rutherford, of course, got very excited and said, "Whoa, are you joking me? It got deflected way over here? Rebuild this whole apparatus and make this screen circular. So you can measure basically all the way over around like this to see exactly where every once in a while the alpha particle nuggets are being scattered off to." So basically, a new device was made. Gold foil. Detector. Of course, I'm drawing the alpha particle much too large, but I'm just trying to show that it's positive too. You know, it's much too large, not drawing the scale here. And again, sometimes hours upon hours would go by and the alpha particles would just go straight through. But every once in a while, at a certain position, the alpha particle would go through and get deflected. Now basically, when it got deflected, the angle at which it got deflected from its main path was measured. This angle right here is called theta, and that's the scattering angle. Most of the time, if the particle went straight through, the scattering angle was 0. That's when the alpha particle went straight through, straight in. But every once in a while, there would be scattering angles up to 90 degrees. And every once in a while, an alpha particle would go missing. So Rutherford said, rebuild the apparatus and make that detector go full circle all the way around. Here we go again. Gold foil. This time the apparatus. All the way around, 360. Alpha particle was shot in, and again, 99.99% of the time, alpha particle went straight through. Every once in a while, one would be scattered, and you get a scattering angle. $30, $40, $50 degrees. But lo and behold, every once in a while now, the two graduate students saw an alpha particle get deflected nearly straight back. If it went nearly straight back, the scattering angle started to reach all the way up to nearly 180 degrees. Rutherford said this is like shooting a gun with bullets at toilet paper and having the bullets come straight back at you. They were shocked. They couldn't believe that these massive alpha particles were being deflected straight back off of this skinny, thin gold foil. Remember, 99.99% of the time, the alpha particles went straight through. But every once in a while, boom, straight back. So basically, let's take a close look at what was going on in here and what Rutherford concluded. So you see this little bit right here? I'm just going to magnify that in. We're going to go take a closer look at that gold foil right there on the next page. And I'm even going to magnify it even more. Rutherford concluded that this gold foil was basically made up of atoms. Whoopsie. Each one of these circles here was an atom of gold. And that dot that I've been drawing in the middle, that was the nucleus of the gold atom. And if that there was the alpha particle, most times an alpha particle would go straight through like that. And what Rutherford concluded was that most of the gold atom was empty space, and that most of the mass of the gold atom was located in these nuclei right here. But the rest of the atom was basically empty space. And that's why the alpha particle could just easily go through undeflected. But if an alpha particle went through, let's say it was shot through like this, so it was coincidentally just shot in really close to the nucleus of the gold atom, then basically it would be deflected because like charges repel. So right in here, when the alpha particle went really close to that gold nucleus, if I redraw that circle over here, okay, here's the nucleus, and here's the alpha particle, and if they were both positively charged, that alpha particle would experience a repelling force. So instead of going straight through, it would be deflected. So it was actually like an electrostatic force that repelled the alpha particle. That's the gold nucleus. And that's the alpha particle. So Rutherford was the first to have conclusive evidence that matter is made up of atoms, and that the atoms are mostly empty space with most of their mass concentrated in a positively dense nucleus. So let's write up oopsies. Observations, conclusions, observations, most alpha particles went straight through without being deflected. Conclusion from that: most of the atom is made up of empty space. Sometimes, rarely, an alpha particle would be deflected up to 180 degrees. Conclusion? Over here I want to say most of atom. Conclusion: atom has a positively charged super dense core. containing most of the mass of the atom. Of course, I'm referring to the nucleus. So, Rutherford model of the atom. Basically, here's the whole atom. With a dense nucleus. Now, J.J. Thomson already discovered the electron, so it was already known that there were electrons in the atom. So basically, Rutherford didn't really do too many measurements, anything about the electrons. He just assumed that the electrons were somehow orbiting the nucleus. But that really wasn't a big part of his model. Bohr went on to do a lot more work with the electrons. So basically, that's the gold scattering experiment.